Yes, we're back and we're still in chapter 6, believe it or not. Still one more lecture after this, actually, but this is where we're going to start to think a little bit more about how things happen in the real world and not make so many assumptions like we have been so far. If you recall in the previous lecture, we would say that, oh, let's assume there's plenty of oxygen to react with the acetylene or whatever the example was, or enough hydrogen to react with the nitrogen when we were making ammonia. Well, in the real world, we actually have to worry about those things, and we call those limiting reactants. If we don't have exactly the right amount or plenty of extra in many cases of a given reactant, then the reaction will stop. So our percent yield, which is how much we actually can make in a reaction, is influenced heavily by what's called limiting reactants. Which one is going to run out first, and when something runs out on the reactant side, we cannot make any more product. If there's multiple reactants required and we run out of one, the other can't make product by itself. So we are going to have to start to consider that, and we're going to make even more use of our understanding of calculations in chemistry to determine percent yields after we have found the limiting reactant. Let's just define a few terms because they will come up quite a bit now that we are trudging into this territory. Theoretical yield is the maximum amount of product which is calculated based on the balanced equation. So theoretical yield, we look at any reactants, we figure out based on stoichiometric coefficients, the mole-mole relationships, how much product we can make, and if we were to make all of it, to convert every single molecule of the limiting reactant into product, how much yield could we theoretically make? The actual yield is the amount of product that we actually obtain, and it's typically lower than the theoretical yield because we don't get reactions to go all the way. Sometimes they just are reversible reactions, so they don't go only in one direction. Sometimes there's a problem with our technique, and sometimes you actually get an actual yield that's higher than the theoretical yield, and that's an indication that you didn't dry your product or you've got contamination or something serious has gone wrong. Percent yield is the ratio of actual yield to theoretical yield, and as a percent you would multiply it by 100 to make it a percentage, and of course as chemists we're all after that 100% yield. We all want to get exactly perfect percent yields, and sometimes we can get darn close. Other times the reactions just don't go the way we would hope, and maybe for a certain reaction a 40% yield is excellent based on the side reactions that can occur and all of that. So just because we don't always achieve 100% yield doesn't mean we're failures. Sometimes it's the chemistry that is the problem, and certainly not us as wonderful synthetic chemists. So as we've done so many times now in the course, let's develop a guide to these calculations for percent yield. First, we're going to state the given and needed quantities. We've done that for pretty much every guide we've come up with. The second step here is going to be to write a plan to calculate the theoretical yield and the percent yield. Next, we'll write the molar mass for the reactant and the mole-mole factor from the balanced chemical equation. And then finally, we can solve for the percent yield by dividing the actual yield by the theoretical yield. That's our ratio, then multiplying that result by 100%. So it doesn't sound too bad, and hopefully after some practice it won't feel too bad, but the first couple of times might be a little rough here, so please pay attention carefully as we work through one of these examples. All right, so let's take a look at this example here. On a space shuttle, lithium hydroxide is used to absorb exhaled carbon dioxide from breathing air to form lithium hydrogen carbonate. What is the percent yield of the reaction if 50.0 grams of lithium hydroxide gives 72.8 grams of lithium hydrogen carbonate? So a couple assumptions here. Let's assume that we're having plenty of carbon dioxide. We've got our astronauts that are breathing out lots and lots of carbon dioxide, so we won't consider carbon dioxide yet in terms of looking for limiting reactants, but we will have to consider that lithium hydrogen carbonate that we start with, that we finish with rather, based on the amount of lithium hydroxide that we start with. Okay, so step one, as usual, we're going to state the given and needed quantities. We'll analyze our problem here to see that we're given 50.0 grams of lithium hydroxide reactant, and we recovered 72.8 grams of lithium hydrogen carbonate product. What we need to know is the theoretical yield of lithium hydrogen carbonate. How much should we have made if all of that 50.0 grams of lithium hydroxide reacted, and then we'll find the percent yield once we find the theoretical yield, because we already know the actual yield is 72.8 grams of lithium hydrogen carbonate product. Our balanced chemical equation, it's misleading, especially if you see a reaction that has no coefficients visible, meaning everything's assumed to be 1. You should definitely check it through, make sure it's actually balanced, because that's a big giveaway that you might have an unbalanced reaction. Here, in this case, it is actually balanced, so we don't have to worry about that. We got lucky here, but please do inspect your reaction equations and make sure they are balanced. If I don't say balanced, or especially if I say unbalanced. All right, moving on to step 2, we'll write our plan to calculate the theoretical yield and the percent yield. So first, to calculate the theoretical yield, we'll do what we're so good at now after the previous lecture. We'll take our grams of reactant, lithium hydroxide in this case. We'll use its molar mass to find the moles of lithium hydroxide. We'll use the balanced chemical equation, the coefficients therefrom, to get the mole-to-mole factor. That will convert us into now moles of lithium hydrogen carbonate product. And finally, using the molar mass of the lithium hydrogen carbonate, we'll be able to determine the grams of lithium hydrogen carbonate product that we should have been able to produce if every single formula unit of lithium hydroxide was converted into lithium hydrogen carbonate. Once we have that theoretical yield, we already know the actual yield. It was given in the problem, the 72.8 grams of product. We'll divide that by the theoretical yield in grams and multiply by 100 after we find that result to get a percent yield. All right, moving on to step 3, we'll write the molar mass for the reactant and the mole-mole factor from the balanced equation. We have 1 mole of lithium hydroxide equals 24.0 grams when you sum the values for lithium, oxygen, and hydrogen from the periodic table. That's the mass of 1 mole of that formula unit. We can put it in either form for its conversion factor. Once we get to step 4, we'll figure that out. We also know that 1 mole of lithium hydrogen carbonate is equal to 68 grams of lithium hydrogen carbonate. So we've got now the extra 44.0 grams from the carbon dioxide. We've done that one a few times. You'll get to know some of these by heart, but again, you just take the 12.0 grams for a mole of carbon plus 2 times 16.0 grams each mole of oxygen, and they would sum to 44.0 grams. Instead of doing it all over again, you can just do that difference. It's just increased by 1 CO2 mole. And we will figure out when we get our balanced setup here which form of the conversion factor we'll use for the lithium hydrogen carbonate. We ran out of space there on the previous slide, but of course the other thing we need to do here in step 3 is use the stoichiometry of the balanced chemical equation to get the mole-mole ratio. And we find, in this case, 1 mole of lithium hydroxide gives yield to 1 mole of lithium hydrogen carbonate. So really, we won't be changing any values. We'll be multiplying by 1 over 1. But for unit's sake, it is important we figure out whether we want the mole of lithium hydroxide in the numerator and the mole of lithium hydrogen carbonate in the denominator, or as we'll see, we need the mole of lithium hydrogen carbonate in the numerator to end up in product moles of that, and finally mass of it, and the 1 mole of lithium hydroxide needs to be in our denominator. All right, here we are in step 4 now, and we can solve for our percent yield by dividing the actual yield by the theoretical yield, multiplying the result by 100%. So first we need to calculate that theoretical yield in grams of lithium hydrogen carbonate. If we start with 50.0 grams of lithium hydroxide, multiply by 1 mole of lithium hydroxide over its molar mass of 24.0 grams. Then now that we're in moles of lithium hydroxide, we can convert into moles of lithium hydrogen carbonate, and then finally multiply through by the molar mass of lithium hydrogen carbonate, 68.0 grams of LiHCO3 per 1 mole, and we end up with a final value of 142 grams of lithium hydrogen carbonate. So if you look at the 72.8 grams that we actually obtained in the reaction, we're about half what the yield should be in terms of theoretical yield. We'll figure that out in the next slide. So we've known the actual yield that was given in the problem, the 72.8 grams of lithium hydrogen carbonate. We just solved for the theoretical yield of 142 grams of lithium hydrogen carbonate. And so now when we find that ratio and multiply by 100%, we find that we actually have a percent yield of 51.3%. So just over 50%, and we did that by just looking at it and seeing the values. But if we're going to actually solve the problem and have a multiple choice answer that we're looking for, we'd expect it to be that 51.3%, the 3 sig figs that we've had in the values for the masses of lithium hydroxide and lithium hydrogen carbonate. So hopefully not too bad, hopefully something that, although it may seem like a lot of work, and it is, once you get used to it, it's really not that bad, and dare I say it, they get to be fun. Personally, I like these reaction types that we find these limiting reagents and theoretical yields. So I just said limiting reactant or limiting reagent, I think I said, which goes by both terms. Our textbook calls it a limiting reactant, and that's the reactant in a chemical reaction that's used up first and therefore limits the amount of product that can form. If we have multiple reactants and one gets consumed completely, then the other reactants can't go on to form product by themselves. They may do some side reactions, and that may be why you end up with a theoretical yield that's, or an actual yield that's higher than the theoretical yield, but again, we do have to consider, do we have enough of each substance to make the amount of product that we expect? Any of the other reactants that we have plenty of, they're called excess reagent, and they would be, or reactant as our text calls them, they would be left over at the end. So most often they'll just stay as unreacted starting material, but sometimes they could react with each other in a different way and make a different product, a contaminating product. Okay, so let's have an example of a limiting reactant. If you think of this example here, how many peanut butter sandwiches could be made from 8 slices of bread and 1 jar of peanut butter? Well, again, if you're thinking that there's typically a lot of peanut butter in a jar, unless you like your sandwiches really peanut buttery, that jar of peanut butter should outlast those 8 slices of bread. If you're making traditional sandwiches, there's a top slice, then there's the peanut butter filling, then there's a bottom slice. So 8 slices of bread should yield 4 peanut butter sandwiches, and that jar of peanut butter, depending on how generous you are in your portions, there should be at least some peanut butter left over in most cases. Maybe you'll run out of peanut butter first, but again, most of us would run out of the bread and we'd end at 4 peanut butter sandwiches, and maybe we could make another 4 peanut butter sandwiches with the leftover peanut butter. Now, if we consider instead of a jar of peanut butter, just a tablespoon of peanut butter, well, for most of us, a tablespoon of peanut butter might be just enough for 1 sandwich. So in this case, it wouldn't be the peanut butter that's left over, but rather the bread. We'd probably make the 1 peanut butter sandwich, use up that tablespoon of peanut butter, and then we'd be left with 6 slices of leftover bread. So the reactant that is the limiting reactant can change based on the problem specifications. If we change the masses, then you have to reinvestigate each of the reactants and see if you have a new limiting reactant. So again, it's not a terribly difficult concept, but it does involve an additional step if we're looking first for the limiting reactant, then finding the theoretical yield, then having the actual yield to find the percent yield. It gets complicated. It's a lot of little steps. None are particularly difficult on their own, but it's a lot to keep together. So hopefully if you approach it that way, where it's just step by step, then you shouldn't have any trouble with even the most complicated limiting reactant style question. All right, so let's look at something that's a little more typical for a chemistry class and not so cookbookish with the peanut butter sandwiches. So this question says, calculate the moles of product, and the product here is methanol, that can form given 3.00 moles of carbon monoxide reacts with 5.00 moles of hydrogen. What is the limiting reactant? So we have our balanced chemical equation here. 1 mole of carbon monoxide gas reacts with 2 moles of hydrogen gas to yield 1 mole of methanol gas. So first, in part A, what mole-mole equalities will be needed in the calculation? B, what are the mole-mole factors from these equalities? C, what is the number of moles of methanol from each reactant? And then D, what is the limiting reactant for this reaction? So basically running through those steps we usually run through where we're analyzing the problem, just this time asked stepwise as questions. Okay, looking at that first question, what mole-mole equalities will be needed in the calculation? Well, we're looking at how much methanol we produce, and we're looking at starting with the carbon monoxide, how much methanol, and starting with the hydrogen, how much methanol. So the mole-mole equalities we'll need in this case will be 1 mole of carbon monoxide equals 1 mole of methanol produced, and 2 moles of hydrogen equals 1 mole of methanol produced. So we'll have to consider each of those because we have to actually solve this thing 2 times to figure out who is indeed the limiting reactant. Okay, now B, what are the mole-mole factors from these equalities? So depending on how we want to represent it, we can have the 1 mole of carbon monoxide in the numerator and the 1 mole of methanol in the denominator, or the inverse. Likewise, for the hydrogen, we can have the 2 moles of hydrogen in the numerator and the 1 mole of methanol in the denominator, or the inverse. Now on to the part C, what is the number of moles of methanol from each reactant? Well, if we take that 3 moles of carbon monoxide and we use the correct form of the conversion factor where we have the 1 mole of methanol over the 1 mole of carbon monoxide, we see that we end up being able to produce 3 moles of methanol, right? It's a 1-to-1 stoichiometric relationship, so the 3.00 moles of carbon monoxide can be converted into 3.00 moles of methanol. For the hydrogen, which we started out with more of, right, we had 5.00 moles of hydrogen, but because it's 1 mole of methanol produced for every 2 moles of hydrogen gas that react, we really can only produce 2.50 moles of methanol from that hydrogen. So even though hydrogen started off in the greater amount, it's not going to give us as much methanol as our carbon monoxide. Now, of course, we can't produce whichever we choose. We can't decide, well, I'd rather have 3 moles of methanol, so I'm going to decide that I want to pick the carbon monoxide as the limiting reactant. Unfortunately, no. We've got to look at which produces the least amount, just like our bread and peanut butter. In the first example, we ran out of bread and we were stuck at 4 sandwiches. In the second example, we ran out of peanut butter and we could only make the 1 sandwich. So we have to be careful about, we can't just say that we would choose the one that gives us the most. Instead, we have to choose the species, the reactant that gives us the least to identify the limiting reactant. And so here it is, the limiting reactant is the hydrogen, which produces the smaller number of moles of product, 2.50 moles in this example. So this was more straightforward than you'll usually see, right? We went right from moles of reactant to moles of product. Typically what we'll do is we'll give you masses, and masses would have been even different because hydrogen's so light that 5 moles of hydrogen would have only been 10 grams, whereas the 3 moles of carbon monoxide would have been close to 90 grams. So we did have a smaller mass of hydrogen, but a greater mole of hydrogen, and it's always the moles that we compare. If I give you masses, you've still got to convert to moles, so it's just one additional step. Okay, and here we just see a nice graphic that shows us that we have the carbon monoxide and the hydrogen in that 1-to-2 ratio producing the methanol. Initial moles of carbon monoxide would be 3.0 or 3.00 if we go based on what the problem itself said. For hydrogen, we start with 5.00 moles, and then we assume we start with no methanol to begin. Once the reaction goes, well, we're going to stop when we use up all of the limiting reactants. So those 5 moles of hydrogen, as we just saw on the previous slides, that would give 2.5 moles of methanol. So we can make the 2.5 moles of methanol by using up all 5 moles of hydrogen, and because the methanol and the carbon monoxide are in that 1-to-1 mole ratio, we'd also end up using up 2.5 moles of the carbon monoxide. And at that point, at the end of the reaction, we'd still have a 1/2 mole of carbon monoxide reactant, and we'd have our 2.5 moles of methanol product. We assume that the hydrogen is completely used up because it's the limiting reactant. And again, so what we can identify here is that carbon monoxide is the access reagent, hydrogen is the limiting reactant, and the theoretical yield, at least in moles, of the methanol is 2.5 moles. All right, so what we just did together, now we see it in the more typical guide form. One, state the given and needed quantities. So typically we're given either moles or mass of the reactants, and either moles or mass of the product is what we're looking for. We use coefficients in step 2 to write those mole factors and to write molar mass factors if needed, and sometimes you'll need them. This previous example we didn't, but in the future we might. Number 3, calculate the number of moles of product from each reactant and determine the limiting reactant. And then finally, number 4, use the molar mass to convert the smaller number of moles of product to grams of product. And then if we happen to have the actual yield, we could even find the percent yield as we did earlier in this lecture. Okay, let's work another example together using that guide, and this one we're starting with masses here. So how many grams of carbon monoxide can be produced from a mixture of 70.0 grams of silicon dioxide and 50.0 grams of carbon? So there's our balanced chemical reaction, and we're looking for the amount of CO that we can produce. We could also consider the other silicon carbide product, but here the reaction specifically asks about CO. So that's the one we'll go with. Step 1, we'll state the given and needed quantities, and when we analyze this problem, we see that we're given 70.0 grams of silicon dioxide, 50.0 grams of carbon, and we need to know the smaller quantity in grams ultimately of the CO2 product from these reactants. Again, we've got to look at the mole-mole ratio in the balanced chemical equation after we've converted to moles. We can't just say, well, we have only 50 grams of carbon and we have 70 grams of silicon dioxide, so we'll run out of the 50 grams of carbon first. No, it's not a mass thing, it's a mole thing. So we've got to convert to moles and then consider the moles of product and ultimately the mass of product from each of those reactant masses. Moving on to step 2, we can write our molar mass factors. We see that 1 mole of silicon dioxide equals 60.1 grams of silicon dioxide, and then we can have the conversion factor with either the mole of silicon dioxide in the numerator and the 60.1 grams in the denominator, or the inverse. For 1 mole of carbon, it's 12.0 grams right off the periodic table, and we can either have the 1 mole of carbon over the 12.0 grams of carbon, or we can have the inverse depending on our setup. Now that we know the molar mass for each of those reactants, we can look at the mole ratio between reactant and product. So first, for the SiO2, 1 mole of silicon dioxide yields 2 moles of carbon monoxide, and then we can have that conversion factor in whichever form is appropriate. We have, for the carbon, 3 moles of carbon yields 2 moles of carbon monoxide, and we can have that mole ratio in either form depending on which conversion factor helps us to cancel our units correctly in our setup. Okay, moving on to step 3 now, we can calculate the number of moles of product from each reactant and determine the limiting reactant. So starting with the 70.0 grams of silicon dioxide, if we multiply that by the 1 mole over its molar mass, we can get the grams to cancel. We're now in moles of SiO2, and if we multiply by 2 moles of CO per 1 mole of SiO2, we can now cancel the moles of SiO2 and be left with 2.32 moles of carbon monoxide being possibly produced. For the carbon, 50.0 grams of carbon times 1 mole of carbon over 12.0 grams of carbon times the 2 moles of CO per 3 moles of C gives rise to 2.77 moles of CO. So the limiting reactant must be the SiO2 because it produces the fewer moles of product. We have to consider the same product in order to determine the limiting reactant, and here the one that produces the least amount of that CO is our limiting reactant. And even though we had a higher gram mass of the SiO2 and a mole basis, at least in terms of how many moles of CO it can produce, it produces less than the smaller mass of carbon. So there we have it. We've identified the limiting reactant. Now finally, we can move on to step 4, where we use the molar mass to convert the smaller number of moles of product to grams. So we've identified the SiO2 as the limiting reactant, and so with the knowledge that 1 mole of CO equals 28.0 grams of CO, we can take our 2.32 moles of CO that the SiO2 would produce, multiply it through by 28.0 grams of CO per 1 mole of CO, and we end up with 65.0 grams of CO as the theoretical yield. Some students find it easier in the previous step to just go to mass of each and then pick the smaller mass. That's fine, but really, once we know the smaller number of moles, obviously it will generate the smaller mass. So you only really need to take the moles of the true limiting reactant, the moles of the product that would produce, and multiply it by the molar mass. So there we have it. Loads of work for that 65.0 grams of CO. And again, in a multiple choice question, a relatively simple looking question with some fairly simple looking answer choices could involve quite a while for solving it. So I won't have too many of these on the exam, but you might expect to have at least one question asking about limiting reactant. Okay, why wait for the exam when we can try this out right now? So in this learning check, we're asked if 48.2 grams of calcium are mixed with 31.0 grams of nitrogen, how many grams of calcium nitride can be produced? And we have our balanced chemical equation showing 3 moles of solid calcium react with 1 mole of gaseous nitrogen, dinitrogen, one of our diatomics. We just call it nitrogen, but we understand it to be N2. Yields 1 mole of calcium nitride solid. So go ahead and based on those masses of starting material, figure out which reactant gives the smaller moles of product and therefore find out the mass of product from that limiting reactant. Pause the video here. It'll probably take you some time as you're still getting used to this. When you're done, start back up and we'll see how you did. All right, so hopefully you did this well, but let's run through the solution just in case you got hung up on one of these steps. Step 1, of course, state the given and needed quantities, analyze the problem. Here we know that we're given 31.0 grams of nitrogen and 48.2 grams of calcium to start, and we're looking for the smaller quantity, ultimately in grams, but first in moles, of the calcium nitride product that we get from each of those masses of reactant. We have, of course, the balanced chemical equation at our disposal as well. Moving on to step 2 here, we're going to use the coefficients to write mole factors, and of course we'll use molar mass factors here as well. So 1 mole of calcium is equal to 40.1 grams of calcium right off the periodic table, and we'll either express that as the 1 mole of calcium in the numerator and the 40.1 grams of calcium in the denominator, or its inverse. We also know that 1 mole of nitrogen, dinitrogen, equals 28.0 grams of N2, 14.0 grams for N, and 2 of those 2 moles of N to get 28.0 grams for a mole of N2. And we can have that 1 mole of N2 in the numerator with the 28.0 grams in the denominator, or we can have the inverse depending on which allows for cancellation correctly in our setup. All right, we also know that 3 moles of calcium equals 1 mole of calcium nitride from the balanced chemical equation, and we can have that expressed in whichever form the conversion factor allows for the proper cancellation. Probably need that 1 mole of Ca3N2 up top and 3 moles of calcium down below in order to get moles of calcium nitride and then finally mass of calcium nitride. Likewise, 1 mole of nitrogen gives rise to 1 mole of calcium nitride. So we can either have the 1 mole of nitrogen up top and the 1 mole of calcium nitride in the denominator, or as we'll find, the 1 mole of calcium nitride product over the 1 mole of nitrogen reactant is the form we'll actually use. Okay, so taking those masses, first the 48.2 grams of calcium multiplied by 1 mole of calcium over 40.1 grams of calcium to convert into moles of calcium, and now finally multiply that through by 1 mole of calcium nitride per 3 moles of calcium to cancel out the calcium and determine that we can make 0.402 moles of calcium nitride from 48.2 grams of calcium. When we do the same process with the 31.0 grams of nitrogen, multiplying through by 1 over its molar mass, we find that when we convert into moles of calcium nitride, we end up with a theoretical yield of 1.11 moles of calcium nitride based on that amount of nitrogen to start. So even though nitrogen's in the smaller amount, and it has a smaller mass and is in a 1-to-1 ratio, it ends up giving us actually almost 3 times as much calcium nitride product as the larger mass of the calcium, which required 3 moles and therefore gave us far less. So the limiting reagent in this example, limiting reactant as our book says, is calcium, which produces 0.402 moles of calcium nitride. And finally, moving on to step 4 here, use the molar mass to convert the smaller number of moles of products to grams of product. And so we see here we arrived at that 0.402 moles of calcium nitride. We'll multiply by the form of the equation 148.3 grams of calcium nitride, which we arrived at by taking 3 times the molar mass of calcium plus 2 times the molar mass of nitrogen from the table. When we sum those up, we get 148.3 grams of calcium nitride per 1 mole of calcium nitride. And the conversion factor in that form allows us to cancel moles and be left in grams of calcium nitride, and we find 59.6 grams of calcium nitride can be produced. Hopefully that's the value you arrived at. If not, please do practice these some more. Please reach out to me if I can be of help. Otherwise, I'll see you soon for the last part of Chapter 6 lecture.